All right, let's come to order. You can continue this after class. Actually, so I do have a little demonstration of audio distortion I want to get to today. I did start recording. Thank you for the reminder, though. Of course, you won't remind me when I forget to record, right? So we want to talk about another, again, this whole chapter is amplitude modulation. I want to talk about, it's called double sideband, and sometimes it's called suppressed carrier or without carrier, and that's way too long to write. So double sideband suppressed carrier. Okay, there is also, or DSBSC. So there are also single sideband methods, and we've talked about standard AM radio and what that looks like. Take your baseband signal, multiply it by a cosine, really, or actually we take our baseband signal, add a DC offset, multiply that by a cosine to generate our AM radio wave. What that does is it takes our baseband spectra, translates it up around FC, and then there's also an impulse at that. And that impulse is actually just the DC offset that's modulated up to FC. Okay. But that DC offset is what allows us to do envelope detection of the waveform, right? Because we can just follow the peaks with a simple rectifier and recover the message. So really inexpensive receiver. It's wasteful of power. That most of the power, like 2/3 of the power, is actually in that impulse that carries no information. So someone pays for that transmitted power. It's the radio station. Well, ultimately, it's the listeners because they pay for advertising, right? Or the advertisers support it. You go to the advertisers. This method is much more efficient in power. There is no actually wasted power here. There's nothing, there isn't a carrier component. Unfortunately, it requires a much more expensive receiver. Not that much more expensive these days, but 20 years ago, these double sideband receivers were a couple $100 or more compared to under $10 for an standard AM radio. So mathematically, though, double sideband is actually simpler than even standard AM radio. We just multiply our message by our carrier. Two pi FC of t. And this is all that you have to do to generate double sideband suppressed carrier. Just multiply by a cosine. Okay. So no DC offset added. Okay. Now what that means is that we can't actually use envelope detection with this. We'll get a distorted version of the message if you try. So the spectrum here is AC over 2. Again, multiplication in the time domain becomes convolution in the frequency domain. The cosine is a pair of impulses at FC and minus FC. So this just becomes so this is what the spectrum. So again, I'll try to draw some pictures to the best of my ability. First in the time domain, saying this is what the message looks like. The trick for drawing the message times the carrier, the only difference with AM radio, we added a DC offset so that the message plus DC offset never went negative. We're not doing that now. So I'm going to try and draw this thing again. and then draw the negative of that. Okay. And then what the actual transmitted waveform is, it's this times, cosine, this thing going between plus or minus 1. So this would actually be, AC times whatever the height of, let's call this AM, and it varies between plus AM and minus AM. So this would actually be AM AC over 2. And then and again, in real life, the frequency of the carrier is much greater than I've drawn it here. So the period of the carrier would be much smaller. These zero crossings would be much closer together than I've drawn in this picture. Now it looks like, well, you can kind of see the message there. Unfortunately, you can't recover it using envelope detection. Envelope detection follows this positive peak, right? So out of an envelope detector, what you would get is this, which is and what we want to recover is that. There's really no way to know, though, is this the part that's supposed to be negative, or is that? There's really no way to know. Okay, so you can't use pure envelope detection to recover double sideband suppressed carrier. We have to use something else. Fortunately, mathematically, it's even simpler, but it's more expensive. Okay. So, but now in the frequency domain, and let's assume MF looks like this: plus W minus W F, and so the modulated message has a spectrum like this: FC minus FC. Okay. What's the width of the modulated spectrum? It's just that there's no frequency scaling or anything like that. It's this thing just slid to the right. It's still 2W. My drawings are compressed, or it looks like compressed, but it should be the same bandwidth, actually. Again, this little demo we'll look today at seeing how that is, seeing a shifted version of that. As is this. Now, what's the bandwidth of standard AM radio? 2W as well. There's no bandwidth savings here. We'll talk about single sideband methods. Again, and with real signals, these are reflections of each other. So the upper sideband and the lower sideband both contain the same information. So can we get rid of one of them? Yes, we can. Again, the receivers become even more complicated. What's the difference? What's the main difference in the frequency domain between double sideband and standard AM radio? There's no impulse at FC, but it's that impulse that allows us to do envelope detection. That's the DC. That's the DC component here, the DC offset that gets translated up there, and it's that DC offset, that shifts this thing up so that we can do envelope detection and recover the message. So same bandwidth as AM. We're going to look at what happens in the tone modulation case before we look at how to recover double sideband suppressed carrier. Again, we'll look at tone modulation for kind of all of the different analog methods that we look at. So we'll do this with FM radio as well. So, and it's an easy case to set up in the lab too. By the way, in your first project, The first part of it is standard AM radio and using envelope detection for standard AM radio recovery. The second part is actually double sideband suppressed carrier. And so you have to use you can't use envelope detection. I think in the project, I have you use the envelope detector for the double sideband. You'll get a distorted version of the signal. You should get a distorted version of the signal in that case. And then I have you use the double sideband receiver, which we haven't talked about yet, okay, which should give you a better sounding output, okay. So I think in that project, and again, I'm going from memory here, or what the project should be, maybe not what it actually is, but I think I have you use the standard AM receiver and the double sideband receiver, but then applying the standard AM modulated message and then the double sideband modulated message to both receivers. Okay, so you should get two outputs for each case, one that should sound good, the other. Actually, the double sideband receiver works fine for standard AM radio. You'll see why. But the envelope detector doesn't produce a good result for double sideband suppressed carrier. So our double sideband suppressed carrier then would be, mathematically, if I just could remember the trig identity for the product of two cosines. Does anyone happen to remember that? It's 1/2 cosine of the difference plus 1/2 cosine of the sum of the arguments. Okay, so it's ACAM over 2 cosine of 2 pi. And it doesn't matter whether it's FC minus FM, which I'm going to write it like that because the carrier frequency is much greater than the message frequency. That will give me a positive result here, but cosine of minus theta is the same as cosine as plus theta, so it doesn't really matter. And then I pulled the half out here, cosine of 2 pi, then FC plus FM of t. So this is actually the lower sideband component, the part that's below FC. This is the upper sideband component, the part that's above FC. So in the frequency domain here, I get an impulse at FC minus FM and at the negative of that, and at FC plus FM and at the negative of that. So F minus FC plus FM plus delta F plus FC minus FM. So, and then plus AC AM. And you could combine these terms differently, but delta F minus FC minus FM. So this is the component that actually is at FC plus FM plus delta. And then this is the mirror image of that component. So if I were to draw this, again, what M of F looks like in this case, because it is a sinusoid, I get a pair of impulses at plus or minus FM. And they would be height AM over 2, right? That's just the Fourier transform of AM cosine. It's a pair of impulses at FM minus FC. We know what modulation does. It, multiplying by AC cosine of 2 pi FC, it just slides that picture to the right. And that's what this long, nasty mathematical formula represents. FC plus FM, FC minus FM, And then the other part of it would be the components at minus FC. Okay. And the height here would be AC AM over 4. The Fourier transform of M of t gives us 1/1/2. The Fourier transform of the cosine gives us the other factor of 1/2. So together we have that factor of 1/4. So again, this is kind of like standard AM radio. Our message is modulated up around the carrier. In this case, it would look like these impulses. But there is no impulse at FC like we have with standard AM. So the other thing that we look to compare these different messages or modulation techniques is how much power is transmitted. In this case, the power in the lower sideband, and actually you could get that directly from here. This is the amplitude. So it's going to be the amplitude squared divided by 2. Okay. So that would be AC squared, AM squared. 2 squared is 4, divided by 2, that gives me an 8. Okay. Remember, that's the power in this cosine. It's the amplitude squared divided by 2. And then we have the same power in the upper sideband term. So the power in each sideband is given by this expression. There is no carrier power here, which was the third term that we had for standard AM radio, that other impulse. This is all the power that's in that transmitted message. And it's much less power than AM radio. So this is actually better suited for two-way communication, where you have to have AM transmitters on both ends, AM transmitters and receivers. Unlike AM radio, right? You never transmit through your AM, you never use your AM radio anyway. But if you did, you never transmit from your car back to the radio station. It's one-way or broadcast radio, right? One transmitter to many users. This is more appropriate for portable, battery powered, because it requires much less power than standard AM transmission does. Okay. So it's better for portable communications, low power communications, two-way communication. Okay, well, we've already said you can't use envelope detection for it, so how do you recover it? It's actually kind of neat. It's simple. It's called using a coherent detector. So in these different modulation methods that we use, we'll look at with AM, FM, and also some of the digital modulation techniques, there are coherent detectors and non-coherent detectors. They usually don't use the term incoherent. That has another meaning, but non-coherent detector. The envelope detector is an example of a non-coherent detector. The difference is, for a coherent detector, you have to recover the carrier at the receiver, and we'll talk a lot more about that. But with an envelope detector, we don't need to know the carrier frequency, okay? At least not precisely. It's never in our little envelope detector. It's just a diode and capacitor. Here you'll see for coherent detection, you have to actually recreate the carrier somehow. You have to know the carrier frequency. That's not quite as easy as maybe it sounds at this point. So, but the assumption is, at the receiver, in this case, I'm going to call it AC prime cosine of I'm going to say right now that this is, replica of the carrier. Doesn't necessarily have to have the same amplitude. At this point, I'm saying it's FC. It's exactly the same frequency as used at the transmitter. But this is now my receiver. And then the output of this is VT. And then I run this through a low-pass filter to produce the output. So we want to take a look at that. So again, one of the key giveaways that you've got a coherent detector or a coherent receiver. Sometimes you'll also hear the term synchronous and asynchronous. So synchronous is equivalent to coherent detection. Asynchronous is equivalent to non-coherent detection. Typically, those terms are used more with digital modulation techniques. Okay. But a giveaway that you've got a coherent detection is if you see some sort of sinusoidal generator in your receiver that is generating a sinusoid that's somehow matched to the carrier frequency. Remember in our AM radio receiver, at this previously with the envelope detection, we didn't have this, right? It just came in, we did rectification, and then to recover the peaks of our AM radio signal. So let's look at how this works. We'll look at it again in the time domain. The time domain, again, depends on a trig identity that involves the multiplication of two cosines. Surprise. So this is S of t, our received signal, right? This is what our transmitter generated. Now, again, at the receiver, AC is going to be much smaller than it is close to the transmitter antenna. The farther you are away, the smaller AC is. So it's not really the same AC. You'll see AC doesn't really matter here in recovering the envelope. I've got a volume control. So VT is ST times this sinusoid that I'm generating at my receiver. So it's AC prime, AC, MT, cosine squared, 2 pi FC of t, or cosine squared. Again, that's cosine times cosine. 1/2 cosine of the difference. Cosine of the difference would actually be cosine of 0. So that's 1. So I get, again, I'll get these two terms of a half here. Let me factor that out. I'll get MT, and then I'll get cosine of the sum, again, times MT. So that would be 2FC T. And then, so again, we'll take a look at this in the frequency domain. But what is this? This is my baseband message, right? It's an amplitude version of my baseband message, my M of t. Okay. Remember, at my transmitter, I multiply by cosine 2 pi FC to produce the modulated signal. My receiver, multiplying by cosine again, reproduces the message. Okay. Plus this other term, which is actually if you look at this is MT modulated to 2FC. Right? A very high frequency. So after low pass filtering, after LPF, VO of t is AC prime AC over 2 M of t. Okay. I've recovered my message here. Okay. I want to draw the frequency domain pictures. So again, let's assume M of F looks like this. W minus W, and then say it has a height of AM. So what does the transmitted signal look like? S of F. Well, that's AC over 2 plus FC. So again, we know what that looks like. FC, that's this thing up here, minus FC. It's translated to the left. It would actually be AC times AM over 2 with a width of 2W. So the highest frequency here would be FC plus W. The lowest frequency would be FC minus W. Okay. So this is what I get at my receiver. Now, V of F is, again, I'll give you the mathematical expression for it here. V of F is the Fourier transform of V of T. So I've taken this S of T, multiply it by, again, essentially the carrier, again, that I'm trying to reproduce at the receiver. So what that would look like is AC over 2, AC prime over 2, times my received signal shifted to the right by FC and shifted to the left by FC, right? This is S of F. Okay. I'm going to multiply by a cosine again. So I multiplied this by a cosine, got the baseband spectra shifted to the right by FC, shifted plus it shifted to the left. This is what gets transmitted. At the receiver, I multiply by a cosine again, same frequency. That's going to shift now this thing to the right by FC. Then we add to that a version of it shifted to the left. So this is where, when I plug in my expression for SF here, I get AC prime AC over 4, and then I'll get MF minus 2FC plus MF plus MF. That again comes from, if I substitute in F minus FC for F here, I'll get M of F plus M of F plus 2FC. Okay. Or AC prime AC over 4 MF minus 2FC plus 2MF plus MF plus 2FC. Again, that's the math. That's one way to visualize it. The other way to visualize it, again, is, let's look at the spectrum. The other way to visualize it is I'm multiplying by cosine. So I shift this to the right by FC. So that will give me this. And then another component now at 2FC. Okay. That's this picture shifted to the right. I'm going to have AC AM over 2 times AC prime over 2. So I'm not going to really worry about the amplitudes at this moment. AC prime AC, then 4, and then I called this AM, the height of this thing AM. So that would be that height at this point. And that would be the height of the other, that component that's up at 2FC. Now that's part of it. The other part is this thing shifted to the left by FC. Right? So that gives me this component now at minus 2FC, same height. And then I'll get this thing doubled here. okay, an identical version of it. So when I add these two together, I don't change the width. Okay. This would now be AC prime, AC, AM over 2. Okay. And it still has a width of 2W. I'm going to pretend we run it through a low-pass filter. I'm going to assume it's ideal here. As long as the bandwidth of my low-pass filter is greater than W, really the only purpose of it is to knock out these two high-frequency spectra. Right? When I do that, you know, the final result here would be this. I think I call that V0 of F, 2W in the frequency domain. But this is exactly like my original spectrum, except for the amplitude scaling, which you can control that with a volume knob. Okay. So pretty simple mathematically, simpler even than AM radio. I just multiply by a cosine again on this thing to recover and run it through a low pass filter to recover the message. But practically, it's a little more difficult. So let's talk about, there's a couple of things here. I've assumed that I'm able to create exactly the same frequency at the receiver that I used at the transmitter. That's not an easy thing to do, okay? Even with two function generators in the lab, sitting next to each other, trying to get them adjusted to exactly the same frequency is not easy. Now, with crystal oscillators, it can be a little better, but they're never going to be perfect, okay? And these things are typically widely separated, okay? So how is this done in practice? In practice, they will typically add a little bit of the carrier, not as much as used in AM radio, but add a little bit of the carrier to the transmitted signal, and then recover that at the receiver using a bandpass filter, okay, to regenerate this and multiply them together. But it's a more expensive process. But do we have to do that? How close do I have to be? Can I just use a completely independent function generator? It's not just the frequency. Okay. I have to also be matched in phase, right? I have to turn them on at exactly the same time, if they're actually generating cosine waveforms. If I don't start them at the same time, there's going to be a phase shift between the sinusoid that's used at the transmitter and the one that I used at the receiver. What's the effect of that phase shift? So we could have two forms of mismatch. If there's a phase mismatch, then C prime of t is AC prime cosine of 2 pi FC of t plus phi. Then if you go through this, VO of t is AC prime over 2 cosine of phi m of t. Maybe not too bad, okay, because this is just a number, right? It's just a constant, cosine of phi. Now, what is this though if that angle is 90 degrees? At 0, then I get nothing out of my receiver if one is shifted by 90 degrees. If there's 0 phase shift, then there is no phase mismatch, and there's no scaling here. Okay. If this is a 90 degrees, it doesn't matter how much you turn the volume up on a 0 degree signal, you're going to get 0 degrees. So this phase mismatch can cause between no distortion at all and then complete loss of signal. And then typically, The phase shift might vary with time a little bit, so it may fade in and out, as it goes, the times where it's relatively close, but times where it may be closer to 90 degrees. For frequency mismatch, C prime of t is equal to AC prime cosine of 2 pi fc plus delta f times t. Then, if you go through the math, VO of t is AC prime over 2 cosine of 2 pi delta f t mt. So again, delta f here, if the frequencies are close, this is should be a relatively low frequency signal, but it's modulating the amplitude of your message. Okay, so there are times, if this is when this is near its peak, there's essentially no distortion at all. But when this crosses 0, then you've lost the signal entirely. So it would sound like the amplitude's getting larger and smaller as time went on. So again, if delta f is 0, there's perfect match. This is 1, there's no distortion at all. But with a slight frequency this mismatch, you'll notice some modulation and amplitude. Okay, I wanted to that can also be picked up as modulation of MT, right? This is multiplying by cosine. So it can be looked at, another way to look at it is a change in frequency of the message, a slight modulation, maybe by 10 hertz, 100 hertz. Remember, we're working up in the megahertz range here. So it's not unusual with 2 separate oscillators to have, 1,000 hertz difference in the frequencies produced by the 2 signals. So what I have here is just a little demonstration of the different types of modulation or distortion that you can get. So I put these up if you want to download them and play them. But this first part is just reading in a message. It's a sound clip from a movie. And then the periodogram is a way to display the Fourier transform. Okay. So we'll see a graph of the Fourier transform. That's the plot here. And then it plays the original message. So there's some this is in MATLAB Octave how you actually play that waveform. S is my message. You have to use this audio player and then play it. And then, probably the simplest type of distortion is just to play the negative of the signal, right? So, wherever you have a positive hump, that becomes a negative hump. Okay. Now, typically for an audio signal, you can't detect that, with your ear. The negative of the original audio signal and then the negative of that, okay? Which means that usually for audio, it's okay to use an inverting amplifier. Remember, you've used op amps and you've got inverting and non-inverting. So for audio, it's usually not a problem to use an inverting amplifier for audio. It can be a problem for video though, where if you've got blacks are low and whites correspond to high voltages, if you invert those, then you get the negative of your image, right? For audio, it tends not to be a problem. Unless you're dealing with something like stereo, and one is negative, goes through an inverting amplifier, and the other goes through a non-inverting, they would actually cancel each other out. So probably the simplest type of distortion. S here is one long column vector. So flip up down would actually time reverse the vector, flips it vertically. Okay. If it were a row vector, you could use flip LR. Okay. What's the effect of that? That's time reversal. That sounds interesting. It sounds like some sort of alien language. Okay, so that's one form of distortion. Then I looked at, I think also in here, this would be a slight frequency mismatch, just of 1 hertz, right? So modulation of the signal by 1 hertz. It's really, you can't hear much distortion there, I don't think. And then 10 hertz, I think I do 100 hertz. What's surprising is that these are still intelligible. You can hear the distortion, but you can understand what's being said. Okay. 100 hertz. And then I use a square law detector, which is really just like, it's similar to an envelope detector, but it's easier to implement in MATLAB. It's really the only reason. So, but I think in the first case, square law detector, where I don't have enough of a DC offset, so I get distortion. And then in the second case, I make the offset equal to the peak value in the signal. And so it sounds pretty good. You really, that would be an envelope detector for a properly modulated signal. And then I show the signal actually multiplied by a 10 kilohertz signal. Really, oddly enough, you can still kind of hear this. This is still in the audio range. Remember, for radio, we're modulating with signals that are up in the megahertz range, well out of the hearing range. You can kind of hear this, but really I wanted to do this one so you could look at the Fourier transform of the signal. You'll see that the message is actually shifted up to around 10 kilohertz. You'll see that when we look at the Fourier transform. This is then actually using a double sideband recovery. You know, multiplying by 10 kilohertz and then multiply it by 10 kilohertz again should recover the signal after actually low pass filtering. So let me actually go back to the command window and we'll run this. This is the negative. This is the time reversed. This is modulation by 1 hertz. Really can't tell much of a difference. This is by 10 hertz. You can hear a little bit there. A little bit of distortion. This is 100 hertz. You can definitely hear some distortion there. It's kind of surprising it's still intelligible. This is the distorted envelope detection. So this is envelope detection, presumably without distortion. So it should sound pretty good. This is modulating by 10 kilohertz. But again, the idea here was, this is like double sideband modulation. The idea there was to actually show you the spectrum, which I'll talk about in just a second. Then I played actually the signal after multiplying by a cosine, and which sounded pretty good because the 20 kilohertz is actually out of the hearing range. And then after running it through a low pass filter. Okay. So what do we got going on here in the frequency domain? Well, you know, this is a real signal, so you know, a bunch of different frequencies present, and you also have noise that's present. And what this is showing is essentially the one-sided spectra. So, you know, if I try to repeat that, this is what the Fourier transform would look like, okay, of the original signal. Now, this is the Fourier transform after modulating by 10 kilohertz. Not AM modulating, double sideband modulating, right? And again, it's just one-sided spectra, but what I've what I've argued is that what you should see is this thing shifted up to 10 kilohertz. And then, again, it doesn't show the negative frequency. So, and that appears to be what's going on here, right? This baseband signal that's now modulated up to 10 kilohertz. Here, I multiplied it by a cosine again, okay? And then that's where we should see this thing up to 20 kilohertz, but also back down to 0, okay? So this is actually double sideband recovery, where we multiply by a cosine again, and then run this through a low-pass filter to actually hear the original audio. So I'll play it one more time. It only takes actually a minute. Again, I'm using much lower frequencies. What's the movie? You don't know? What the heck is the movie? With Chris Pratt, and he's got Guardians of the Galaxy, yeah. With Rocket, yeah. They've got these websites that they've got all these different clips from various movies. So I think has anyone done the project yet? I'm pretty sure that was a movie clip too, wasn't it? Lord of the Rings, maybe? Shrek. All right, that's it for today. So see you on Wednesday. Thank you.